right, guys, and welcome. We're getting into inequalities today. That's right, inequalities. We've seen a few of these symbols on homework so far. You've dealt with them in the past, so we're just going to get back in with them, looking at one variable inequalities today. So here's our introduction of the class. We're going to use some equation solving skills to help us today and make sense of inequalities and what solutions, specifically what solutions can be to a particular inequality. So let's get started now and let's check this out, this very first problem, question 944. All right, it says, as a class, create a human number line, for each of the following mathematical sentences. You will be able to assign a number to represent the number line. When your number makes the equation or inequality true, stand up to show that your number is a solution. If your number does not make the equation or inequality true, remain seated. Okay, so you might be reading this here and you might be thinking, how the heck is this possible? And you know what, I'm perplexed too. How is this going to be possible? We're not in class right now. We got this whole social distance learning right now. What can we do? Oh no, I don't know if we're going to be able to do this human number line. Who can we rely on for this? Let's think about this. I think we need, when a situation comes up where we can't solve them, we got to think, who do we normally turn to? Who could salvage this situation and help us figure this whole conundrum out so we can actually do this lesson? Oh, wait a second. What's that noise I'm hearing? What is that? Do you guys hear that too? Listen carefully. What is that? What's going on? Who is that? I think it's happening. Wait, they're coming for us. Wait, they're coming here? They're coming to our social distance learning lesson? That's right, these folks plus some other ones. We got some DC characters, some Marvel characters. Oh my god. Yes, the superheroes are here, I guess, to save the day. Let's do this. We got not just the human, normal, and a normal year I do the human number line with my classes. This year, we're doing the superhero number line, I guess, because we have some volunteers. So superheroes, I put the call out. Come on here, assemble yourselves. Assemble yourselves at the front of the class, and let's do this superhero number line right now. Put out that call, and they're coming on up. Welcome, superheroes. Thank you for joining us today. From Reg 2104, I have my superheroes. So it's not just any number line this year. It's not just a social distancing number line this year. It's a superhero social distancing number line. Gathered ourselves up. We have our numbers. And we're going to explain what are solutions. Okay, so we're going to go through all these. A, B, C, D, E, F, G, H. Superheroes, you ready? All right, you're ready. Okay, so they're going to be a number line, right? Just to remind us of the real number lines and the real number systems. Any real number can be assigned a point on the real number line. We have it. Maybe we put a 0 there. You don't necessarily have to put 0 there, but the idea is that numbers are getting more positive as we go to the right on the number line, and they're getting more negative as we go to the left on the number line. And every single real number is represented, including the numbers you see above us on our superhero number line. And the in-between numbers are included as well. So even though we don't have it in our assignments right now, in terms of superheroes, there would be like a negative 3.5 here. There would be a negative 4.5 here. There would be negative decimals, positive irrational numbers like pi. Pi would be here, right? 3.14 and non-repeating, non-terminating decimal would be there. So what we care about today is what you're going to go into with the first day of lessons is one variable inequalities. You're going to look at one variable inequalities like this, and you're going to learn or refresh yourselves on how to graph the solutions to a one variable inequality like this. So superheroes, you're going to help demonstrate this. What you're going to do is you're going to hold up your number or numbers if you're holding more than one number, if that number could be a solution for X in a statement like this. Very first one right here. Normally, superheroes, I think they'll be very quiet today actually. Yeah. They work in mysterious ways. Normally, I'd have the humans in the human number line read out the inequality in class, but instead, I will read it for the superheroes, and superheroes will raise their numbers if it is a solution. All right, A here. X is greater than or equal to negative 2. Please raise it up if you have a solution for X, if you're holding it. Very well done. Superhero number line. Okay, that looks pretty good. That looks like we noticed several solutions to the inequality X is greater than or equal to negative 2. Number 2, X is less than or equal to 1. Our 1 is getting eaten here, so that means our X's, all of our solutions are less than or equal to 1. 1 should be the biggest number represented. Yes, 1 is being held up Everything below that is being held up as well. So our number line looks like it might have a border at 1 and might go below. Oh, is this an inequality? No, it's not. I'm circling this one. Which superhero or superheroes is going to take care of us here? As a solution to x equals 3. Raise it on up. That's right. Hello there. All right, next one. X is greater than or equal to 0. 0 holding it? 0 holding it? Yes, 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 superheroes. Well done. X is greater than 0. Let's keep going. Ooh, we got another equation here. So how many of the superheroes are going to be holding up solutions to this one? Thank you very much. Thank you very much, superhero. That is indeed the one and only solution to x equals 2. Okay, getting a little bit harder down here is this thing. This is called a compound inequality. This is a math sentence where we have not just one, but two inequalities. And these inequalities, there's another word for inequalities called constraints. And a constraint is a limitation or a restriction. And here there are two restrictions on what x can be. So if we were to read this, picture how you'd read this. You see the less than or equal to symbol right here, and -1 is less than or equal to x, which is less than or equal to 4. So x is constrained. It has both a lower bound value and an upper bound, right? It's bounded by those -1, 4. So superheroes, will go ahead and raise it on up. If you were a solution to the statement, -1 is less than or equal to x, which is less than or equal to 4. Which is x's would fly? Which x's would be solutions to that statement? Well done, superhero number line. Man, these superheroes, they're taking care of us today. Taking care of us. All right, another tricky one here. Ooh, we got to think. Okay, so superheroes, think about the numbers you have, right? That's x there. If you square that number, x squared, is that greater than or equal to 4? Ready, set, go. Superheroes, lift it up. Lift up those numbers. Interesting. Interesting. How many boundaries do we see there? How many boundaries? So who's not raising that? Okay, well, in the middle? Oh, in the middle? Interesting. Okay, so think about how that might be drawn on the graph. That looks kind of interesting. Okay, it looks a little bit different than some of the other ones we've been seeing. And finally, wow, superheroes. What will we do without you? How about h? X is less than -3. Ooh, I'm looking at -3 right now. -3, you holding it up? Not holding it up? You're good? You're not holding it? Okay. All right, good. All right, x is less than -3. Think about that. How is that one different than x is greater than or equal to 0? X is greater than or equal to -2. What's going on there? Where's our boundary? Is our boundary at -4? Really? Is that the first number that's less than -3? I don't know. All right, well, thank you, superheroes. We got a little visual demonstration of the old real number lines and how to maybe represent solutions to inequalities on those real number lines. And that'll be today's lesson today, and we'll get into some tough edge cases where the answers might not be completely obvious, but if we study the math, we'll get them, we'll feel good about them, and know that we're following the right processes and getting to ourselves to the right answer. So let's do this now. Thank you, superheroes. You're not the heroes we deserve, but you're the heroes we need. We appreciate it. Alright, so we just finished out this number line. So hopefully you got a sense of what an inequality solution looks like. If you had an inequality, take x is less than or equal to 1, for instance. We got this 1 right here. These guys were all standing up. 0, 1, -1, -2, and 1. Those superheroes right there. Well, these aren't superheroes. These are just humans right here. They were all standing up. So you have kind of multiple solutions to an inequality. X equals 3, who was standing up on that one? Well, that was just that guy right there. Okay, there was only one guy standing up in that one. So down here, it's just having you think about what your answers, how your answers are going to be different in this part of the chapter versus what you've been seeing previously. So earlier in the book, the most amount of solutions to a particular problem we would have was 2. A quadratic equation or an absolute value equation, actually, right? We usually have 2 solutions. There's going to be way more than that with something like this, okay? So it says here, compare the solutions to an inequality like x is greater than or equal to -2 with that of an equation like x equals 3. What's different? What causes it to happen? Well, x equals 3. Let's start with x equals 3. There was only one solution there. So if we looked at this actually on a number line, let's maybe look at this real quick.
in a number line. So when we have just one variable, I just need to draw my x-axis. That's it. I just need to draw one dimension here to locate where my solution is on this number line. So I don't need to worry about an x-y axis because I only have an x here. So I'm going to find 0, I'm going to find 1, 2, 3, go up to 3. We could have 4 here, right? Your solution on this number line is just going to be on that point 3. And I'm going to make it real big, but I'm going to shade it in because this should just indicate to you that our solution here is just on that 3. It doesn't include actually the decimals that this kind of overlaps with. We kind of ignore that, right? It's kind of impossible to show exactly just 3. And miss 3.1, 3.2. So it doesn't include 3.1, doesn't include 3.2, it just includes exactly 3. There's our solution to x equals positive 3. So a lot different here with this x is greater than or equal to negative 2. That was the very first one. All of these folks, all these superheroes in our video, were standing up. So that means that all of these numbers are solution. So I'm going to go ahead and shade this in because this is how you graph something like this. Again, we just have one variable, so x is greater than or equal to negative 2. So I just need one dimension here. The left-right dimension is what I need to do to sketch this out, to sketch out my solution region to this problem. So negative 2. And I'm going to go a little further than what our number line had up here. And I'm going to put negative 3, negative 4. These are not solutions here. So the thing that your graph showed were that all of these were solutions. I'm going to put points down. So there was a point down, a solution of 3. These would all be solutions to x is greater than or equal to negative 2. All these people were standing, right? I have a point here, a point here, a point here, and a point here. Okay, but was that all of the solutions? Like if I had a 4 here, right? All these people were standing up because we went to 3. If I had a 4 here, should I put a point there? Yeah, I definitely should. 4 is definitely greater than or equal to negative 2. Negative 2 is greater than or equal to negative 2 because negative 2 is equal to negative 2. That's one thing, is that this is inclusive here. You can be greater than or you could be equal to, and it's totally fine, right? So if you're equal to, it's also a solution to this. Let me put this here. Negative 2 is greater than or equal to negative 2, right? So that's why negative 2 is standing. Are these all the solutions, though? Is this a way to show it? Well, I should just keep going. I should put the shade in 5. I should shade in 6. Wait a second. What if I did this a point here? Would this actually be true in this situation? I did put this one directly in between negative 1 and negative 2. If I put negative 1.5, is that greater than or equal to negative 2? Which one's smaller? Which one's closer to negative infinity? That's closer to negative infinity. Negative 1.5 is closer to 0 on the number line, so it's greater than negative 2. So that should have been included. This should have been included. And in fact, what are all the points that should be included? Oh, it's all of these points here. You should shade in. So if you're going to graph, this is called graphing the solution region right here. Graph solution region to this inequality, x is greater than or equal to negative 2, is you're actually going to shade an infinite amount of numbers one direction. This is called a ray in geometry, right? A ray. You're going to have an endpoint, and then it's going to go one direction or the other for something as simple as this. It'd be more complicated for something like that, right? X squared is greater than or equal to 4, and also for this one where we have a compound inequality. Compound inequality means more than one, right? More than one inequalities in a given statement. So this is for a simple inequality, and this is a little more complex inequality. This is a compound inequality, it'd be a little bit different. Okay, so then the next question is, how many solutions does an inequality such as x is less than or equal to negative 1 have? Infinitely many. And I can draw that out and show my solution region by doing this. I got my 0 here. I want to go to 1. I'm going to show the 2, but I don't really need to write in the rest of the numbers. Let's check it out here. So x can equal 1, right? 1 is less than or equal to 1 because it's inclusive here, right? X is equal to 1. Either one is fine, right? It doesn't have to be both. It can be either one. Either it's less than or it's equal to, and it's fine. It's a solution. So I'm going to fill in, I'm going to close a circle at 1 because we're allowed to be 1, and we're also allowed to be anything less than 1. So it would be all of these points here, okay? So this would suggest that x is allowed to be 0, and that would be a true statement. 0 is less than 1, or less than or equal to 1, so where it's okay. Negative 1 is less than or equal to 1. That is also a solution. Negative 5.3 is less than or equal to 1. So it's a solution. Negative pi, right? Negative about 3.14 or so, that's also a solution. So everything shaded, you have to shade small numbers, right? Shade left, okay? Shade left to represent all solutions to x is less than or equal to 1. Next question, how is the result of negative 1 is less than or equal to x is less than or equal to 4, different from the other inequalities? What about the result of x squared is greater than or equal to 4? This one we saw when we did our superhero social distancing number line, when we did negative 1 is less than or equal to x is less than or equal to 4. Only a few people were standing up. How this was different was that they were standing up and it went kind of in the middle here. Negative 1 was standing up and up to 4 was standing up. 5 wasn't standing up here. So that's how it's going to be different on this. We're going to go from negative 1 and we're going to go all the way up to 4. And this is inclusive. When you see the bar underneath, it means inclusive, less than or equal to. Negative 1 is less than or equal to x. That means x is allowed to be 1. That would be a solution in this compound inequality. And the largest, so this is sort of the minimum here, the maximum is over here. You write it this way, left to right, you're going from minimum to maximum, because negative 1 is less than or equal to x, so x can be negative 1, and x is less than or equal to 4, so that can go up to 4, but it can't go beyond 4. So we have what these dots here are called boundary points, okay? So how it's different is that we have 2 boundary points in a compound inequality that's written like this. Not all compound inequalities will have 2 boundary points, but this one definitely does. We can't go beyond 4 because 5 is not a solution, 6 is not a solution, 7 is not a solution, negative 2 is not a solution, negative 1.1 is not a solution, but those are not solutions. Okay, so let's get the other one down here. Let's see what this one would look like. So this one was a tricky one when we did our superhero number line. X squared is greater than or equal to 4. Who was standing up on that one? Let's see if we can figure this out. Was 1 standing up when we did x squared is greater than or equal to 4? Well, 1 squared is 1, and that is not bigger than 4, right? That's not greater than or equal to 4. How about 2 squared? Okay, 2 squared was standing up, right? 2 to the second power equals 4. So that would fulfill the inequality. 2 squared would be greater than or equal to 4 because it equals 4, and that would be a solution. So we'd have a boundary point. The point of equality, right? This is something to point out. The point of equality, when you figure out what you can put in for x that'll equal the other side, that was where your boundary point's going to be. So we have one boundary at 2, and I'm going to close a circle because I'm going to do a closed circle here. It's called a closed circle because x is allowed to be 2, and it would be greater than or equal to 4 because it's equal to 4. So it could either be greater than 4 or it could be equal to 4, and that would be okay. That would fulfill the solution. Was 3 standing up? Yep, 3 was standing up. So 1 wasn't standing up, but the other side of the boundary was standing up. And in fact, every other number larger than 2 would return a square that is 4 or above. And that would be part of our solution. Who else was standing up? Here's where you need to be tricky. Like, it's tricky here when you have more complicated ones. You got to think through. You got to test big numbers. So here, x could be a very big number, and it would be greater than 4. What's another thing that would get us something greater than 4? Very, very big positive number. What if we test a very big negative number? What about negative 10? If we plugged in negative 10 for x and we squared it, what do we get? We get 100, and 100 is definitely greater than or equal to 4. And negative 10 times a negative 10 would be a positive number. 2 negatives multiply together, make a positive number, and negative 10 times negative 10 would be 100. So we'd have to go down here to negative 2. We'd have negative 3 right here. And so we would need another filled-in boundary point and shade all solutions lower than negative 2, right? Negative 3 would be a solution. You just reason through more of them in your head. Negative 3 is definitely a solution here because negative 3 times negative 3 is positive 9, and that's greater than or equal to 4. Okay, so now you got the point, hopefully get the swing of things here, right? You know how to take an inequality and then show the solution region. This is just called graphing it, right? Graphing the solution region. So here, we actually see the graphs. It says write an inequality that represents the solution shown on each number line below. So here we want to find the boundary point. At this point here, x equals 1. That's good here too. And then x equals like 1.1 here, x equals 2, x equals 3, x equals 4, x equals pi right here. So it looks like x can equal 1 or x can be greater than 1. So our solution here is going to be x can be greater than or equal to 1. There's our solution to A. Part B is a little bit different. It's still tricky. We haven't come up with this too much yet. Just once in the superhero number line for this guy. It's tricky guy here. So we had to think about that one. Who was standing up on that one? Well, all of these fine folks here were standing up, but not -4. Was -3 standing up? Was -3 less than -3? No, -3 equals -3. So it's kind of similar to that. So here, can x equal 1? In this situation, what does an open dot mean? What do you think here? Well, I pointed to, when I had a closed dot right here, I said x can equal 1 because we see it on the number line. Do we see 1 represented on the number line? We have an open dot. So open dot stands for non-inclusive. This should definitely go in your notes. Open dot stands for non-inclusive. Closed dot, if we see it filled in, it stands for inclusive. So what that means is that our inequality symbols that go with non-inclusive, when we see an open dot like this, our symbols will either be less than or it'll be greater than, because all the solutions need to be above or below where the boundary is. And we'll write the answer to this in a second. A closed dot like this one, this was inclusive, so that's why we used this inclusive symbol right here. Greater than or equal to, or less than or equal to. The solutions are all bigger than 1, but it can be 1 too. Here, this is at 1, but all solutions, they're all smaller than 1. It cannot be 1. And when we see the open dot there at 1, this just means that x cannot be that. It cannot be 1. At 1 is not a solution here, okay? But x can equal 0. It can equal -1. X can equal -3.5. X can equal that. So all of our solutions for x need to be smaller than 1. Need to be smaller than 1. And open circle, non-inclusive. Non-inclusive symbol will not include the boundary point. Just the solutions will be below the boundary of x equals 1. This one here, if we're following along the logic here, it looks like x can equal 3, and it can equal stuff smaller than 3. 2, 1, 0, -1. That direction, x is less than 3. Here, right? This is less than, we're going this way. There's actually one trick to this you may have learned before. I'm going to do this here. I don't realize what I'm doing. What am I doing right here? What did I just draw? What does this look like? I couldn't really do it. Let me draw it like this. We have the variable to this side. Hey, we can make an arrow. Check that out. So this is x is less than 3. I made an arrow. Pretend you make an arrow out of this. This actually reflects what the solution region is. Pretty neat there if you can follow along this. So if you have the variable on the left side, this is a shortcut, a trick to make sure you did this correctly. You can draw in your less than symbol and you can be sure you did this right because you're shading left. Okay, this is shaded left. And we see a less than symbol, meaning you can make an arrow pointing to the left, which is pretty neat. Here we shaded left. Look, we could have done the same shortcut here. We could have put not a shortcut, this is more like a trick to make sure you did it right. It's pointing left. If x is over here, all of our x's are to the left of 1. All of our x's are to the right of 1, including 1. We have the inclusive thing here, but that's because our arrow, if we turn the inequality sum into an arrow, it points to the right. So it's just one quick trick to making sure you did the problem correctly. Let's look at this one here. Can x equal 4? No, x cannot equal 4, so we have a boundary there. Cannot equal -4, so we have a boundary at -4, but x needs to be above that. So I'm not going to put my inclusive symbol down here. X is greater than -4, or -4 is less than x. And x can equal 2. Okay, so we have a boundary point at x equals 2, and it's inclusive. So it can't be beyond 2, so I'm going to put my inclusive symbol here. X is less than or equal to 2 because 1, for instance, is wedged in between those, right? X can be 1. -4 is less than 1, but less than or equal to 2. And this would be our solution to D, and hopefully you got this for C as well. All right, now we're grooving. Let's keep going. Now we're grooving, we're moving. Let's get some more done. With your study team, find at least 5 x values that make the inequality true. let's do it. What do we think? So we have 3 here. It needs to be greater than this. So we're looking for big numbers. It needs to be bigger than 3. So why not some big numbers? How about let's try out 10? How about that? 10 work. X could equal 10, 20, 30, 40, 50. 40, 50. Let's see if that works. So 2 times 10 is 20, minus 5 is 15. Yep, that's greater than or equal to 3. 20 would bring us to 40, minus 5, that's 35. That's greater than or equal to 3. 30, yeah, that's the right deal. That's 55 is greater than or equal to 3. 40, 80, 75 is greater than or equal to 3. Yeah, these are all solutions here. Okay, those are all solutions that X can be. Big solutions. So we have to shade to the right? We have to shade to big positive values to get our answer here. Okay, how many solutions are there? Sure, infinitely many. Right, I just picked 5 off the top of my head. But I could have had decimals, I could have had irrational numbers as long as we were bigger than whatever the boundary point is, which we have to solve for there. All the way up to positive infinity, we'd be able to figure out solutions. What's the smallest solution for X? This point is called the boundary point, okay? So what you need to do to get the boundary point, you actually need to solve for it. Solving for boundary point. Okay, solving for boundary point. So what I was trying to show you on the last problems is that your boundary point is going to be a point of equality, right? A point of equality. And a point of equality here. Or a point where you cannot be, but it's still going to be close to the solutions of the problem. So anyways, to get the boundary point in this situation, we're looking for the smallest value. The smallest value that's going to make the left side equal to 3. Because the left side could be greater than or equal to 3. So whatever value of X here would make the left side exactly equal to 3 would satisfy the inequality. It would still make the inequality true. And even if this wasn't greater than or equal to, it would at least show us where the boundary is and show where our solution region would kind of begin. Okay, so for solving for a boundary point, what we need to do is to change to an equation. Okay, equation means let's actually switch this to an equal sign and solve that. And that's why we call this solving for a boundary point. So I want to do that below. 2x minus 5 equal to 3. And if we can solve this equation, I know you all can solve these kind of linear equations right here. They're not that hard. It's going to show you where you're going to put that point on the number line, where your solution region begins, and then we're just going to have to shade to the right of that, right? We're going to have to show that all 5 of these plus infinitely many more are actually solutions. So let's solve this right now. Plus 5, and we get 2x equal to 8, and then x equals 4. Here's where our boundary point is. Smallest solution for x is going to be 4. 4, plugging that in there, would make the left side equal to 3, and that's still greater than or equal to 3. So what's the significance of the boundary point? What's the relationship with the inequality 2x minus 5 greater than or equal to 3? The boundary point is it's the smallest value of x that satisfies the inequality. Yeah. Write an inequality that represents the solutions for x. On a number line, highlight the solutions for x. Be ready to share your number line with the class. Okay, so up here we've confirmed that x being 4 is part of the solution region. It's allowed to be 4 because that makes it 3 greater than or equal to 3. And then x could be 10, x could be 20, x could be 30. So at the x equals 4, that's again called the boundary point. And we could be all solutions above and including 4, including that boundary point, because our symbol is greater than or equal to. Okay, so our solution here in this problem, once we get our boundary point, so we figure out the boundary point, know that all points larger are solutions, and then we can reflect that with an inequality. X can be greater than or equal to 4. Notice here, it's actually the same symbol in this problem. It's not always going to be the same symbol. That's why you got to think through it. You got to figure out which side of the boundary point are solutions, because it's not always going to be the same symbol. And we'll see trickier ones later with that. Okay, is this a trickier one? This might jog your memory a little bit of something. But solving linear inequalities with one variable. Analyze the process for solving an inequality such as this by addressing the questions below. So I'm actually going to solve this two ways, and I'll do that in a second. But let's read what the problem has here. It says, the key point to start with is the boundary point. How can you quickly solve for this point? Once you have determined your strategy, find the boundary point for this. Okay. So remember, solving for boundary point, change to an equation and solve. So we're going to do that. So this will be the point of equality. When this side equals that side, we'll know that there'll be either an open circle or a closed circle on the number line. Up here, we should show the number line. I think I forgot to do that. But this will be an inclusive because x can equal 4 and all values greater than that. We got our number line done there. So we need to get similarly the number line done with this in a second. So first step, solve for boundary point. So I'm going to do 3 minus 2x is equal to 1. So let's just see what's going to make this equal to 1, and that's going to be the close to the highest value on the number line. So I'm going to subtract 3 from both sides. Again, start away from x. Negative 2 is being multiplied to x. 3 is being added to that. So you do reverse PEMDAS. Addition comes near the end of PEMDAS. So you start with that first if you're solving. Solving follows the order of operations that are opposite to plugging in, for instance. So 3 minus 3 is 0. And then you can end up with negative 2x equal to negative 2. And then finally, you divide both sides by negative 2. Because you have negative 2x's, now you got 1x. And x equals, this just equals 1 right here. X equals 1. So there's our boundary point. Part B, decide if the boundary point is part of the solution to the inequality. Well, the inequality, if now I have my left side, if I plugged in 1 for x, then my left side would be worth 1 because this is the point of inequality here. And 1 is not less than 1. So x cannot equal 1 to be a solution. So it is not part of the solution. If it is part of the solution, indicate this number line with a filled-in circle, a closed circle point. If it is not a solution, show this by using an open circle as a boundary point. Okay, so I'm going to do an open circle. X can't equal 1, so I'm going to put an open circle right there. I'm not going to fill in. I'm going to indicate this is where my boundary point is, but don't include it as part of my solution that I'm reporting to you guys. Next question. Finally, to determine which side of the boundary the solutions lie, choose a point to test in the inequality. If the point is a solution, then all points on that side of the boundary point are part of the solution. If the point is not a solution, what does that tell you about the solutions? Write your solutions to that as an inequality and represent the solutions on a number line. So let's do this. So we need to test a point over here and test a point over here maybe to see which ones are solutions to this. So how about we test x equals 2? How about we test that to see if that's a solution in the inequality? So I'm going to test if x equals 2 is a solution. So I'm going to plug that in to my original inequality. And so now I'm going to actually follow PEMDAS because I'm plugging in. So multiply first. Negative 2 times 2 is negative 4. And that's less than 1. So 3 minus 4 is a solution because negative 1 is less than 1. So x is equals 2 is a solution. So that means anything higher than 1 is going to be a solution to this. If we try 3 in this, we would have 3 minus 2 times 3. That's minusing 6. And that would be negative 3 on this side, which would be less than 1 and also be a solution. If we tested something lower, actually a really good one to test is testing 0. So testing 0 makes it easy to figure out what the left side of the inequality is going to be worth. If we plug in 0 here, it's really easy. The nice thing about 0 is that you get a 0 product with this. So 3 minus 2 times by 0 is less than 1. This would be 3 minus 2 times 0, and 2 times 0 is just 0. So 3 is less than 1, and that's a false statement. This is not a solution. All right, so without further ado, let's graph this bad boy. Again, we have one variable, and that being x, so we're just going left, right? One variable, we're going one dimension. Two variables, right, are x and y problems, right, are functions problems, or just x-y relationship problems. We have an x-axis and a y-axis. So here I've just drawn my x-axis. Boundary point is at 1. Again, we have an open circle open circle like we showed earlier when I was just showing the boundary point. And we test the solutions above the 1. So we shade above, we shade to the right, we shade to the right. And this was a tricky one if you were trying to solve this one here. Actually, like a lot of people try to solve inequalities. This one was a little bit tricky because if you actually just tried to solve this, and I subtract 3 from both sides, I get negative 2x is less than negative 2. You might have thought, hey, I'm going to have to shade below this. I have to shade below this because if I divide both sides by negative 2, I would get x is less than 1. Okay, and that didn't actually match up to what our solution is. Our solution here is x is greater than 1. That is our solution to that inequality. So wait, this goes back to what I was telling you earlier. What happened to the signs? What happened to the signs from our original inequality where we had a less than symbol? Now we have a greater symbol in the solutions for x, our simplified solutions for x. Well, this is a rule, right? This is a rule that you may have heard before doing this. It's a tricky thing with inequalities. But when you divide, so in this one here, we need to divide both sides by negative 2. When you divide by a negative, you need to flip the signs. You need to change the direction that it's going. When you divide by a negative, or actually if you multiply by a negative to both sides, you would also have to change the signs, okay? So multiplying or dividing by a negative, you flip the direction of the signs, because if this side were less than that side originally, right? Negative 2x is less than negative 2, then the opposite would be true. That positive 2x would have to be greater than positive 2, because this would be like a more negative number, right? It would be like negative, let's see, let's test the solution right here. Like if x were like 5 or something, that would bring us down to negative 10, and that would definitely be less than negative 2. So when you divide by negative 2, all of a sudden, big inputs for x, you would need to have big inputs here pointed this direction to have this actually be solutions, okay? So when you divide by a negative number or you multiply by a negative number, you got to flip the signs. That's just a rule you got to remember if you're solving them this way. So I would recommend doing it the way the book does it, okay? Which is 1, solve for boundary point, and then 2, test solution region. And your solution region for an inequality like this, where we don't have any squaring or opposite values or anything like that, it's just going to be one direction of the boundary point. And here's our solution. Final question, 949. With your study team, find all the solutions to the inequality 3x plus 1 is less than 7. Decide how to represent these solutions on the number line and be prepared to justify your decisions to the class. Step 1, solve for the boundary point. 3x plus 1 equal to 7. Subtract 1 from both sides. We get 3x equal to 6. Divide both sides by 3. And we get x equal to 2. There's our boundary point. So I'm going to draw that in to a number line. We have a non-inclusive symbol right here. We have less than, so I'm going to do an open dot, an open circle at the boundary. That's something that a lot of people forget to do, and so make sure you always go back. Solve for the boundary point, and it could be open or closed, and then you got to get your solution region. So let's go ahead and get a solution region. Let's test 0. So I'm going to test x equals 0. That's a good one to test because 3 times by 0 is just going to be 0, and then we can quickly determine that 0 is going to work because 1 is less than 7. So x equals 0 is a solution. It returns that a left side of equal to 1, and that's less than 7. So now I'm going to shade my solution region. Can do that step 3 really, would be to shade solution region and write simplified inequality. That's referring to the solutions. So our simplified inequality here is that x cannot be 2, but it can be less than 2. So this is our final answer. So take a look about that and think about that. And think if you have any questions, email me, comment on this Google Classroom day for day 9, and we should be good. Okay, here's a reminder down here. Make sure you brush up on this. Make sure you know this. Inequality symbols. This came up on a few homeworks before our school closed down and went to distance learning. This is the less than symbol. 2 is less than 5. We got our alligator, it's eating the 5, right? Less than. 2 is less than or equal to 5, or 5 is less than or equal to 5. Those would be valid statements. The larger of the two would be getting eaten, so we know it's less than. And then greater than and greater than or equal to, same logic there. Equal sign is used for equations, and because two equal quantities on one side. Inequality symbols are used for inequalities. So when I say inequalities, we just mean kind of a relationship where one side could be larger or smaller than the other side. So when graphing inequality, because like one side could be larger, it could be smaller, that kind of thing, that means there are a lot of solutions here. So graphing inequality, one variable inequality is going to be on a one variable number line and be filled in circle because this is greater than or equal to. 5x is greater than or equal to 5, be filled in circle. This is also a filled in circle here. Oh wait, no, this is an open circle. So if this is an open, then it would be less than. X is less than -3 for this one here. All right, email me if you have any questions. Inequalities. Hope you enjoy the superhero number line. Thank you to my Reg for doing that. See you later, guys. Bye.